Great. I think we are live with our today's webinar. So I want to say welcome to our webinar about understanding the why and how of 5G narrowband IoT capacity for satellites. I'm very excited that you're here today. We have a full pack program prepared for you today. But before we dive into the topic and what you can expect for today, let me give you a little bit of input why we have come up with this webinar. As you might know, we are a software company here at Gatehouse Satcom, and we are actively contributing to the 3GPP standards. And often when talking to customers, the term capacity is in the room. And I'm sure that René will add a lot of aspects to why capacity is important from technical perspective, as well as how to calculate it. But from commercial perspective, it also plays a major role because it's actually the stepstone in order to understand what is your satellite system capable of. For example, what number of devices can it support? And this is actually a KPI that would be fed into a business case. And then after the business case, this would lead into further strategic decisions. So, for example, how can you monetize your spectrum? Is it possible to serve the amount of devices that you'd like to serve, or doesn't it make sense to go into this technology? And how can you maximize your channels? And so basically, capacity can be a major stepstone in order for commercial and strategic decisions, as well as for architectural decisions. If you need to understand, can your system support 5G NB IoT and with what capacity? But that being said, for the commercial framework of today and the importance of addressing capacity for 5G narrowband networks. And I'd say before we dive into the topic, let me introduce us, who is sitting here at the table with you today, and what we have prepared for you. So, hi again, I'm Julina Hilsch, and I'm Sales Executive here at Gatehouse Satcom. And my background is truly commercial, so that's why I'm very happy to have my colleague René on board.
Hello, I'm René. I'm a research engineer here at Gatehouse. Been here for 1.5 years now, straight out of university, where I finished my PhD in wireless communications for IoT, basically.
Yeah, great. And René has prepared a lot of slides for you today and is also here to answer all your questions as much as time allows, where I'm actually on the last point of our agenda today, because this webinar is all about answering your questions and is also built upon the questions that we have been receiving in advance from you. So while we go through the webinar, if you have any questions, please just type it into the chat you should see in your window. And don't be surprised if you only see your comments. This is just how the tool is set up. We will make sure that we see all your questions. And should we not be able to answer all your questions during the webinar, there will be the answers and FAQ sent via your email afterwards. So that being said, we have a quick introduction about who are we at Gatehouse Satcom, so that you all know what we are doing and why we're holding this webinar. And then we're diving into the topic of the why and how of 5G NB IoT end-to-end capacity. René will touch upon the elements of the capacity, how to calculate it, and then it was also really important for us to go through some real-life examples for a GEO and a non-GEO scenario. Yes, I think this was the most important one. I hope you are very excited now to move forward in the webinar. Maybe as a last organizational remark, as I indicated, the FAQ will be sent to you afterwards, and so will the recording of this webinar. So would you like to rewatch what we are talking today, or see the slides again? You will receive everything via your email. All right, let's get into it. Who are we at Gatehouse Satcom? I'll try and make it short and sweet. Like I said, we are a software-only company. We have been around since the late 90s, so quite some years, and our focus have always been satellite software. For a few years now, we have started to contribute to 3GPP to really help define and contribute to defining the 5G narrowband IoT standards for satellite systems. And our commercial end goal is what we are working towards and developing towards, to have 5G commercial waveforms for satellite systems, no matter what satellite type. And we are also developing the software for the UE stack, so for the end devices. And that's basically what we help our customers in order to go live with 5G services. We also know that the standards are still being developed. So until then, we help our customers to understand how can their system support 5G, what is the capacity, is, for example, actually a question that we help customers with. And we do this all for narrowband IoT, but also eMTC and new radio. And yeah, I think I'd leave it for this. You're always very welcome to reach out to us, look more about how we have helped, for example, Omnispace in our recent feasibility study, or read about our other contribution regarding 5G. Now I'd like to give the word to René to talk capacity.
Okay, well, thank you, Julie. So, yeah, let's start from the very beginning of what is actually the non-terrestrial network. What is the service that you can provide with the non-terrestrial network? So if you watched our previous webinars, you probably have a good idea. So let me go very quickly over this. There are different new service categories being introduced by NTN in a 3GPP context, at least, where you have ubiquitous coverage, where you can have truly global coverage with a single satellite in LEO orbit, for instance, or a couple of geostationary satellites placed to cover the entire globe. You have scalability, which is due to the large coverage area that you find in NTN, very large cells, so you can have very large scalability with broadcasting services, for instance. And then you have service continuity, which is a service case where you can have your coverage when you travel between terrestrial cells. So if you're in a very rural area and you go outside of the, let's say, civilized region, then you might still have connectivity through a satellite cell. So all of these, let's say, opportunities also bring some technical challenges, which is, of course, the movement of bees in low Earth orbit and medium Earth orbits. This introduces Doppler shift and delay, and also makes tracking a whole lot more complicated than it is in terrestrial network. There's a large distance to these satellites, of course, which introduces delay. And then we have the large coverage areas, which gives us the opportunity for multicast and very scalable multicast, but it also gives us a potential very large number of UEs that we need to be able to serve. So today the talk is going more into this direction of figuring out how to share the resources in the radio access network between this large number of UEs. Thank you. So the basic architecture of NTN NB IoT, as it is defined in release 17, which has now been released by 3GPP, is defined now. This has traffic going between UEs and somewhere on the internet or another UE connected to the network, by having the UE connected through our radio access network, as you know it from terrestrial cellular networks, to a satellite, which is connected to the ground station by a feeder link. Now, this feeder link is essentially a copy of the service link. And all that is done from the ground station to the satellite is to shift this feeder link or the service link in frequency. This is because we're dealing with what is called a transparent or bent pipe architecture. This is quite important when we talk capacity, because if the feeder link is available, then the capacity will be equal to the capacity in the radio access network, because the feeder link is just a copy of the access network. And if the feeder link is not available, you will have no service link or no radio access network available. So the radio access network is the bottleneck in this setup, and everything in the backbone behind the ground station can be assumed to be fibers, optical. So this is why we look at the capacity of the radio access network. And today I'm going to go over this very simple to show you some example results in the end. But I'll give you the abstraction of how we model it, and not so many equations into how we model the specifics of it. But basically, the radio access network can be seen as a series of channels, as a series of channels where the UE has to use the different channels as it goes through procedural steps in accessing and using the network. These channels are allocated resources, and resources are time frequency resources. So as you see on this figure, you kind of have a grid, and you divide the resources between the radio access, the uplink and downlink data channels, which also carry signaling or control information apart from application payloads. And you have some overhead in system information broadcasts, other broadcast channels, for example, paging. And yes, as I mentioned, a UE would have to go through a procedure in order to transmit something, for example, a data ONS procedure, as it's known, where it will start by sending a random access preamble, getting a response, and then exchanging signaling information, and in end appending its data payload to an uplink transmission. Or for the downlink, it would the NOB would append the payload to a downlink transmission. So this is the basic abstraction. Mm-hmm. Can have the next slide. Yes. So each of these procedural steps or channels, let's say, can be viewed, as in the figure, as a funnel through which all of the traffic in the radio access network moves. So there's a little bit of a difference between whether the traffic is machine terminated or machine originating traffic. Machine originating traffic has no need for paging, of course, but if we are trying to reach, or mobile terminating, if we're trying to reach a mobile, then we would, of course, need to patch the mobile to let it know that it needs to go through the rest of the steps and receive some data. So basically, the capacity of each channel depends on how many resources are assigned to the channel and the specific link and fading conditions that the UE is experiencing. So this has to do with our satellite configuration, our radio access network configuration, of course, and our fading environment. Yes. So we need to take all of these into account in order to model each stage. And when we have modeled each stage, we can kind of see if any one of them is a bottleneck, and we can trade off resources according to our service scenario. And that's the basics of our framework.
Yeah, and I think that's actually also a good point to highlight that it really depends on in what area do you want to have your services and what is your satellite system, because there is no one answer to what is the capacity, right? It really always depends on these factors that you just mentioned.
Yes, and our framework here is something we use to do analytical models for each step, and then be able to analyze the capacity, right? You could also do it by simulation, but simulation takes a long time to implement, let's say, and then if you are changing something about your scenario, it's very fast to get results. But this analytical way, you have more, you invest less time in implementing everything from the start, and then you can run the analysis a little faster. Let's take the next slide here.
Mm-hmm.
So yes, example results. So I'm moving on very fast now. So all the sub-models, let's say, of the framework, I will not be going over in this webinar. Instead, we will show you some results. So for two cases this time, and all the parameters I'm not putting up here. Also, I'm just going to very shortly describe it, right? We have a CubeSat. It's the smallest form factor we could think of. So here it's a 3U CubeSat, more or less a 3-liter satellite. It's cheap. It's very cheap to build and to launch. It has a few years of lifetime. I think I saw 5 years average lifetime for these kind of satellites in LEO orbit. The thing is that they are power limited because you don't have a very large power budget. You can't fit a lot of solar cells on them or batteries within them. They have a very good uplink power budget due to being in the low Earth orbit. So relatively, at least to other orbits, they are much closer and experience less path loss for that reason. But then you do have the challenges of having a moving EOB, both in terms of Doppler and varying delay, as I said earlier, and also due to the challenges of tracking UEs when the node B is moving around. So having tracking areas in this scenario. All of these challenges have been addressed, by the way, by 3GP. So our assumption is that Doppler and so on will work when you have an appropriate modem. So in the case of GSO, the satellite is much more expensive. They do have several decades of lifetime, at least. And the uplink budget in this case is a little more challenging, whereas in the downlink, you can have much more power and highly directional, very large and highly directional antennas, which also is very advantageous, both for the uplink and downlink. The larger issue is the long delays to GSO, which can be, a quarter of a second in each direction, and having to exchange several messages within one procedural exchange, that can add up to quite a bit. Yes.
I just saw that we got a question towards the packet size we were considering for this one. Can you say anything for this right now?
Yes, we will see some results, but we are considering 50 bytes of application payload, and we are considering it in the MO direction. So that is 50 bytes of payload being transmitted towards the mobile from the core network.
Okay.
Oh, sorry, mobile originating. It's 50 bytes being transmitted from the mobile to the core network. Yeah. Okay.
Okay. Thanks for your answer.
So that's the case, but we can analyze, both directions and any packet size up to 50 bytes thereabouts. So.
Okay. Next slide.
Next slide. Yes. Thanks. So here are the basic link budgets for the two cases. Again, the parameters are not up here, but I attempted to configure the scenarios such that they match more or less towards the cell center. And as you can see here, on the left, you have a CubeSat, which is transmitting a single cell directly underneath the CubeSat. It has a very large coverage area. The scale on the axis are different from the left-hand and right-hand figures. But if we look at the left-hand bottom for the uplink, for instance, the cell width is around 1,000 kilometers down to this 0 dB margin or so. On the right-hand side, you have the GSO cell, and here I have depicted actually a grid of several cells, hexagonal grid. Here, the cells are fixed in time, so UEs don't move as they are going through these procedural exchanges when they're in the GSO case. They do move in the case of LEO. Or non-geostationary orbits. In the GSO case, the beam is much more narrow, and almost all of the uses are concentrated in this region where the link conditions are very favorable. And this is also a large difference between the Cube and GSO cases. Can we have the next slide?
Yes.
So one thing that doesn't depend on, let's say, the link conditions of these satellite scenarios is the RAG and paging stages. These depend only on the RAM configuration. So you might think, what's the special thing about the non-terrestrial networks here? And it is that the load depends on the non-terrestrial scenario. Because you have these very large cells, you can have a lot of UEs you would need to page in order to reach them, or you could have a lot of UEs that would need to go through the RAG stage. So here we need to come up with some configuration. I have done that here. As I recall, the RAG configuration takes up about a third of the uplink capacity, and then it allows for, as you can see, up to 450 UEs, which is quite a lot. And then on the table on the right-hand side, you can see how an overhead of 5% in the downlink could allow for paging up to 800 UEs per second. These are given in rates, so per second. Next slide. So another stage which is much more interesting is the exchange of these procedural messages, signaling data and so on, where we see in the CubeSat case, transmitting this DONAS transmissions with 50 bytes application payload leaves us a capacity of doing these exchanges, that's above 100 times per second in the center of the cell. But as you go towards the edges of the Leo cell on the left hand, you will see this decreasing. And it decreases slowly at first, but on the very edge, it goes towards 0. There's also a tail being dragged behind the cell in the Leo case. This is because our assumption is that UEs, when synchronized to the cell, are able to keep the synchronization. But of course, if they were to start doing their transmissions when the base station has already, the satellite has already flown by them, so they are in this low capacity tail, then they're going to take up a lot of the total capacity in the radio access network, and therefore other UEs cannot use that capacity, other UEs that might be more favorable conditions. So one thing you might do here is to trade off some of the coverage area in order to block or blocking out devices who are not in favorable conditions. On the right-hand side, we have the same kind of plot, but for the geostationary case. Here, we see what I was talking about before on the link budget, that almost all UEs are located in highly favorable conditions. And only a marginal amount are actually located in conditions that are just, let's call it, pretty good. So two very different cases here. If we go to the next slide, I have two CDFs, CDFs for each of the cases again. So it's the same figure as before, just represented now as a CDF. On the left-hand side, for the CubeSat, because the CubeSat moves in time, we have looked into 3 different types of activity. The blue line would be randomized activity from the UE, which we would not expect in the real world, because the UE would know when the CubeSat is present, let's say, or when it expects it to be present, at least for discontinuous coverage. In a grid where there's coverage all over the world, you might expect the blue line. But otherwise, you would expect the green line to be the behavior of the UEs. The red line is an optimal behavior if all UEs only transmit at the time where they are optimally positioned within the flyby of the ENOC B, then that would give you the capacity. Now, the mean capacity here varies between 60, 75 and closer to 100, depending on the scenario. If we look on the GSO case, the mean system capacity is somewhere above 100, so 130, 135 or so. This is quite a lot better than the CubeSat case. But again, very different scenarios. One is clearly much more expensive than the other, right? So this is capacity per carrier, by the way. Oh, sorry, no, it's capacity for one anchor and one non-anchor carrier. Yeah. Okay, I think that's
okay.
Okay, the conclusion here is, as we have said a couple of times now, you need to consider the satellite configuration, the satellite constellation, and the configuration of the radio access network resources, and what type of fading environment you're working in order to get a realistic and precise model of your capacity throughout the system. And then, as a side note, because I didn't get very much into this, you can trade off capacity for coverage and quality of service. So, for instance, if you start sending much larger packets, or you want to transmit with a very high reliability, you would lose some capacity. Whereas, let's say in the instance that you want to trade off some coverage, you can gain some capacity by losing the UEs simply who are not in a good signal condition. So yeah, that's it for the main part.
Great. Now we also get to the other very exciting part then, because I have seen while you were talking that we got a lot of questions in. So I suggest that we go through them now to see which one of them we can already answer now. Even one more coming in. So let's just go through it and you just say stop. And
yes.
we just take a little bit of time to read them carefully as well.
Okay, so there was one coming in just now. When I said one anchor and one non-anchor, what I meant by this is one 200 kilohertz channel for signaling in the downlink, and one 200 kilohertz channel in the downlink, which just has data transmissions and paging on it. In the uplink, all the channels after release 14 are both anchor, non-anchor. They are all considered to have the reg channel on them. So there's 1/3 overhead on the capacity. And yeah, that's it. So the anchor carrier in the downlink is necessary because it holds all the synchronization signals and so on.
I hope this answered the question. If not, or if you have a follow-up question, just type in that.
Should we take some of the earlier questions also?
Yes, we can do that.
And there was one question I also saw that was how are the devices prioritized? So in our model, we assume that there is this grid of resources, right? And then you don't hand resources to each device as time goes on. You compute how many resources does an exchange take up in total. And then we can make an assumption of how well our scheduler fits, this patchwork of UEs requiring resources together. And I think we have about a 90%, what should we call it? A 10% overhead assumption of the scheduler not being able to fit things together. But it could be put to anything in our case. So the UE transmissions are not prioritized. It's just the way we are modeling it. Okay. Yes, so there was a question with the trailing tail in the LEO case, why it's only trailing and not in front of the satellite. So as I mentioned, the UEs in front of the satellite will have to synchronize to the satellite before they can start to consume resources in the radio access network. And our assumption is that once UE has synchronized, it can stay synchronized to the network and then initiate its transmission even when the satellite has passed a bit further away from it. And that's how you get the tail. But you cannot synchronize in advance of the satellite coming to the UE, so you cannot have a tail forward. You cannot have a trailing off capacity forward in front of the cell. The capacity, as soon as the UEs are able to synchronize to the cell, is lower, but it's lower for a short amount of time. Because in this orbit, the satellite is traveling at 7.5 kilometers per second, which is 6.9 kilometers per second on the surface of Earth. So it very quickly comes closer and goes into the region where the capacity is actually quite good in the front of the cell.
Let's see what other questions we have here.
What range of frequencies? So these example calculations were done for 2 gigahertz, so S-band, in both uplink and downlink. What are the typical delays in both, typical turnaround delays in both CubeSat and GSO? So the typical delay in GSO, I mean, I could just give you with the distances, right? It's the travel time, or the travel speed is the speed of light, and the distance is 3,700, I think, for GSO. And for LEO could be 500 kilometers at the low end, and 1,200 kilometers at the high end of LEO. So you can find the times from that, but it is in the order of milliseconds, and it's a quarter of a second in the GSO case for one-way delay, and it is, quite a lot smaller in the LEO case, a few milliseconds. I think 4 milliseconds to 20 milliseconds, depending on how far the LEO is from the UE, okay. Depending on the elevation angle, in other words.
Okay. I also really want to say thank you for all your questions. It's really cool to see, that you have so many, things that you'd like to know. So that's really amazing.
Thanks a lot. Okay. There is a question on the round bandwidth assumed. So what we were looking at was 2 channels. So what would take up 400 kilohertz in the downlink, and the same for the uplink. So the assumption is that every channel is 200 kilohertz, or 180 effectively, but 200 kilohertz, and that there are 4 of them, 2 for uplink, 2 for downlink.
Okay. Let's see what else we have.
Are you assuming the GSO system having several simultaneous GNB cells? Yes, that would be the assumption. So the question here is whether we are thinking that a geostationary satellite would be serving the different beams that it's projecting differently, or it would process them all as being one radio access network. And no, I would have to say definitely you would make one radio access network per beam, and then for each beam you can have a lot of users, right? Because if you I'm not sure how you would mesh it all together in the first place, but if you did, then you would be sharing radio access resources over a lot of different cells. So that would be the same as sharing radio resources between different cell towers, which is, No. So the short answer is yes, we assume that each beam is a cell in its own right in the geostationary case.
Okay, I think we can make it to answer 1 or 2 more questions.
Yeah, so there is a question on the main limitations on the transceiver on the satellite. A lot of follow-up in this question, but the main thing about the satellite configuration, it's hard to say because the answer is it depends on your case, right? As always, there's a lot of trade-offs, but for sure the OFDM modulation, I mean, that comes with a large overhead on the power, because our power amplifiers are maybe 20% efficient, 25% efficient, you know. So you have a large overhead on your power consumption in the downlink, and that is tricky. So you can make up for that by increasing the amount of power on board the satellite. You can make up for it by decreasing the distance to the satellite, so going to a low Earth orbit. Or you could make up for it by putting a very large antenna dish on your satellite. Of course, you can put an antenna on your mobile devices, because that's the whole point of these cellular NTN networks, is that it's going to work with a patch antenna, with an omnidirectional antenna on the UE end.
But so, yeah, basically, there is no typical power consumption that we could name, or?
No.
Okay. Yeah.
I mean, yes, in the LEO case, if you have, if you can output 8 watts, you're okay, probably. If you can output 16 watts per carrier, you should be in a very good place.
Okay.
You can even output 4 watts and get away with it, you know, so having a radio access network. But
yeah, and also because we're running low on time, and also like René said, it depends really on your setup. Should you have any follow-up questions in general on this topic after the webinar, or maybe even for your system, please just reach out to us in either way, and we can take it after the webinar as well, and yeah, help you figure out that topic and question. I think we almost have to close, unless you have seen like any more questions you think we should answer now.
There was a short one on Doppler in the geostationary orbit.
Okay.
In this case, okay, I saw he corrected it to Leo. Yeah, good, because the short answer was in GSO you don't have a Doppler. So can we go a little bit up to the original question? Because
you say stop.
There we go. Stop.
Okay.
Stop. So how is it compensated in the UEs? The UEs also, this is quite technical. I think we'll take this one on the answers to the questions. But very shortly, the eNote B is always transmitting an ephemeris for the satellite. So in the radio access network, when you join, you can read a SIP, System Information Broadcast, specifically SIP 31, which includes an ephemeris that describes what is the current position and velocity of the satellite that's serving you now. So the UE can use this knowledge to predict forward in time where will the satellite be and what will the relative velocity be with respect to the UE. So the UE will compensate in the uplink for this Doppler shift when it's transmitting towards the satellite. In the downlink, the UE is just using the synchronization signals in order to synchronize to the satellite. And then after, of course, obtaining SIP 31, it can do whichever processing it wants to in order to follow. Yeah.
Great. I'd say there's like so many more questions that we actually haven't come to answer yet. But like always, after this webinar, we'll compose the answers to them and forward to you via your email that you signed up with, also including the recording of this webinar in case you want to listen again to some of René's explanations, or also see the slides combined with that. So your questions will be answered. And again, thank you so much for your questions. And yeah, we're also very eager to hear your feedback afterwards. If the webinar really provided you what you were hoping for, what you liked, what you maybe would wish somehow else for the next webinar, and also if you have ideas for other topics that we should answer in a webinar. So please feel free to reach out to me and to you, René. We're always happy to connect. And I think then we could wrap up our webinar, right?
Sure.
Okay.
There are so many good questions.
Yeah.
Okay, we'll answer them on the spreadsheet.
Yeah, we'll do that. Thank you so much for your input, and thank you for joining our webinar.
Thanks.